I'm going to talk to you about pathways towards portable SDR today, and most of these pathways have to do with the RF power amplifier. I'll start off with a brief motivation. This is an architecture that was first proposed by Joe Mottola for his vision of a software-defined radio. And the idea is pretty simplistic, and it leverages the fact that at the time that he proposed this, we had started to get really powerful digital signal processing and computation backends thanks to CMOS. So the Mottola radio architecture is not practical for power considerations because this analog to digital converter that interfaces with the digital signal processing and computation consumes a significant amount of power if we were to try and digitize the entire spectrum from DC to daylight. But it's a very inspirational idea. So I tend to work on the transmit side where we take a digital signal from this DSP and computation backend, send it through a digital to analog converter, and then ultimately a power amplifier. So in Mottola's vision for this software-defined radio, the only purely analog component is the power amplifier. This is a realization of this kind of digital transmit architecture. It is a digital transmitter that consists of an all-digital PLL, some selection logic, a serial interface, and ultimately a couple of RF digital to analog converters. Current art limits the power amplifier implementation to be an off-chip component. And the reason is that CMOS power amplifiers have relatively poor peak efficiency and peak output power. And so they have to be implemented with off-chip components such as 3.5 power amplifiers or 3.5 semiconductor compound devices, which are expensive. So the path to a portable SDR would include implementing a CMOS power amplifier that could be scalable and very efficient. One question we have to ask is why would we use a linear power amplifier if we can leverage CMOS switching performance? So CMOS transistors are not very good linear transconductors any longer. They don't have very high transconductance and they don't have very high output resistance, so they don't give us very good gain. Another thing is that all digital design, all CMOS design for the last number of years has been favored towards making digital-friendly processes, making the transistors very fast switches so that we get very fast high-density logic. So what we want to do is find ways to implement power amplifiers that are digitally friendly to implement. So they have things, they don't care so much about the amplitude of the input of the amplifier and still give us very high output power efficiency performance metrics. So what we're going to try and do is use fast digital correction to linearize the amplifier and give us higher average efficiency. CMOS can never win peak performance metrics, but it can win on an average performance metric. And ultimately, average performance metrics are what matter to the user because this is what really has to do with things like battery consumption from a mobile device. The average metric is what tells us how much energy a wireless device is going to use. Another reason that we'd want to use SDR is that integration lowers cost and makes portability more practical. I can make true general purpose radios if I can implement a power amplifier with a digital transmitter. And true general purpose radios mean that we have lots and lots of volume, which lowers cost in most engineering solutions. So why are linear power amplifiers poor when it comes to efficiency, and why is this important? So wireless demands have been increasing continuously through the years. We now have many solutions that give us tens of megabits to hundreds of megabits per second data rates. And on a single wireless device, we have many different radios. So smartphones have 3 to 6 power amplifiers, 2 bands of cellular, 2 bands of Wi-Fi, Bluetooth, maybe 3G and 4G radios. And the RF power amplifier is the dominant energy consumer. And if we use linear power amplifiers, we have a fundamental trade-off between energy efficiency and spectral efficiency. Why is that? Well, a linear power amplifier, if we look at it over the input envelope voltage that would be expected for a typical communication signal, the linear power amplifier has a peak efficiency when the output voltage is the highest, and the efficiency rolls off as a square of that voltage. Well, if we look at the statistics of a modern Wi-Fi communication signal, if we look at the envelope statistics, which would tell us how much amplitude we're trying to put out of the amplifier, PDF for a 64-QAM OFDM signal is shown right here. And what we see is that statistically, the signal is not going to be operating near its peak value very often. It's typically going to be operating near its average value. And the average efficiency of the linear power amplifier would be very poor at that point. And finally, as I'd mentioned previously, the CMOS power amplifier has low gain because it has low transconductance and output resistance. But digital performance favors a fast switch, and so we should try and leverage that switch performance. What is a power amplifier? Well, a power amplifier is an amplifier that's optimized for power output. In other words, we care about the output power more than we care about other performance metrics, gain or noise figure, and we also care about efficiency. So how do we deliver maximum output power with a transistor? Well, we've probably all seen a set of characteristic curves for a transistor where we have different gate to source bias voltages, and this gives us different current density through the transistor across a drain voltage waveform. What we want to do is provide a resistance to the power amplifier so that we can swing through the entire maximum drain current range of the transistor and its maximum drain voltage waveform. And we do that by finding an optimum termination resistance that is the inverse of the slope between the drain current maximum and the drain voltage maximum. A linear power amplifier, what I mean by a linear power amplifier is an amplifier that for some portion of the conduction cycle, the output voltage follows the input voltage. And it doesn't inherently mean that the amplifier is linear, but for some portion of the amplification, it's operating as a linear amplifier. And I am going to highlight the Class B power amplifier. And the Class B power amplifier is an amplifier that's biased in such a way that the transistor only conducts current for half of the input voltage cycle. So here we have an input voltage waveform, and we see the drain current waveform for the transistor only peaking when the input voltage goes above 0 volts and cutting off when the input voltage goes below 0 volts. And one thing we notice about the Class B power amplifier is that its efficiency is given by this function right here, and we see that it rolls off as a square of the expected output voltage. So this tells us why we get relatively poor efficiency as we scale the output power down from the maximum output power. Another way of looking at this is a linear power amplifier has to have some static bias current dissipation to keep the transistor in its desired region of operation. And so if we look at a typical communication signal, we see the envelope here. And the envelope represents how much energy is being sent to the antenna, being broadcast out into space. And we see that no matter whether the signal is at a peak value or at a valley in its value, it's dissipating some energy. And we see that the ratio of the energy being sent to the transmitter to the energy being dissipated, the area in red, gets pretty poor when the signal goes to a valley. And that tells us why the transmitter has very poor efficiency, or the power amplifier has very poor efficiency. What we'd like to do is find a system that could dynamically bias so that the area that's being, the energy that's being dissipated kind of follows the envelope of the signal. And this would give us pretty favorable efficiency performance on average. So I'm going to start talking about a Class E power amplifier. This is one of my favorites, and I'll kind of tell you why as we go along. But first, what is a Class E power amplifier? So a Class E power amplifier is a power amplifier that is generally called a zero voltage switch. And what zero voltage switching means is that we're going to try and set a couple of conditions on the transistor so that we don't dissipate any energy in the transistor, or at least dissipate minimal energy in the transistor. So what we're going to do is prevent a rise in the drain voltage waveform until the switch turns off. And before the switch turns back on, we have two conditions. First, the drain voltage has to go back to 0, and the derivative of the drain voltage has to be 0 so that we don't conduct current through this capacitor. Now, how do we do that practically? Well, a capacitor is a voltage delay element. We can't change voltage instantaneously across the capacitor. So if we place a capacitor at the drain of the transistor, that would cause a pause in the rise of the drain voltage. So that gives us this delay in our switching condition. And the problem with that is that if we create a voltage delay at this point, then the current isn't going to be in phase with the voltage. Well, that's good at the transistor. If the current isn't in phase with the voltage, that's the condition we're trying to achieve. the transistor doesn't dissipate any energy. But if we try and deliver power to an antenna, we need the current and voltage to be in phase. And so what we do is we have a matching network. The matching network does two things. It transforms the antenna's impedance, which is typically 50 ohms, down to a low impedance, which we need in order to deliver a lot of output power with a transistor. But it also gives us this XOpt term. And XOpt here means that we have some excess inductance, and an inductor is a current delay element. So we delay the voltage waveform using a capacitor, and we have a little bit of excess inductance looking towards the antenna that delays the current so that it's back in phase with the voltage waveform at the antenna. And we can deliver real power out to the world. The problem with this type of amplifier is that it has significant voltage stress, and we'll see why in a moment. One thing that I do want to mention is the reason that I really like the ClassE amplifier, other than the voltage stress problem, is capacitances in MOS devices are native. We get them for free, so we can absorb the capacitance from the MOS device into this network. So we don't necessarily have to add a capacitor to the power amplifier, which is a good thing. So where does the voltage stress come from? Well, if we solve a couple of second order differential equations, we'd find that the peak voltage excursion at the drain node here can be 3.6 times the supply voltage. And that can be pretty bad for a transistor to put a very large voltage across the transistor's oxide layer. We can cause a lot of oxide breakdown. One positive with this is that in a switching, in a switch mode device, the peak voltage waveform happens when the transistor is turned off. So we don't ever have any carriers moving through the channel at the same time that we have a high voltage across the channel. And what that means is that we don't have things like hot carrier effects where current carriers get swept into the transistor's oxide and cause things like threshold shifts in the device. Nominally, we'd like to find a condition where we could keep the stress on a device less than 2 times the nominal supply voltage for the device. And this allows us to operate the device over a long period of time and not worry about breakdown in the device. So we can do some mitigation of the stress in a ClassE network that allows us to take advantage of what's intrinsically good about the ClassE network in terms of CMOS and mitigate that voltage stress problem. So first, we can try and distribute the voltage stress. In a typical CMOS process, fine line CMOS process, we have multiple varieties of transistors, and mainly because we have to drive a signal off chip at some point. So we have thick gate I/O devices. These are used as interface transistors. So if we stack a couple of transistors, we can distribute that peak voltage excursion at the drain node of the transistor across 2 devices. And that certainly helps our stress situation. Another thing is that in 2001, Yu and Wang found that if we use a finite drain inductance, typically this is drain inductance, LD, is chosen to be a very large value. If we use a finite drain inductance, the peak voltage excursion can be around 2.5 times the supply voltage, which basically allows us to mitigate the maximum voltage stress situation on the transistor to the condition when the transistor is off, the thick gate device can handle 2.5 times the supply voltage, less whatever bias voltage we put on the gate, and plus its threshold voltage. And this allows us to operate the transistor up to a supply voltage of 2.5 volts, which is quite good. One problem with a switching type power amplifier is that it has no sensitivity to input voltage. So if we have a signal that has a complicated waveform and it has some kind of amplitude envelope with its modulation, the ClassE isn't very sensitive to it. So we have to find means to interface with a switching amplifier that allow us to achieve linear amplification at high efficiency. This is a solution that I investigated in 2009 while I was interning at Intel, and it's a pulse width and pulse position modulation technique where we convert the complex signal to a pulse modulated signal, and we apply that digital friendly waveform right to the gate of the transistor amplifier. This is an implementation that we performed in 65 nanometers. The problem with this is it is a very digital friendly architecture, but it can only support moderate peak to average power ratios, and the peak to average power ratios reduce as the signal increases in frequency, and we'll see why here. So peak to average power ratio is basically limited by the minimum pulse width that we can transmit through this amplifier. So in a 65 nanometer process, it turned out with a very wide transistor, the transistor tended to become jitter limited and would swallow pulses if the pulse was below a 40 picosecond duration. So what we see is the peak to average ratio that we could support for different frequencies if 40 picoseconds is our minimum pulse width. At 1 gigahertz, we would get peak to average ratios supported of around 18 dB. And if we operated that same system at 5 gigahertz, the peak to average ratio would be reduced to 4 dB. So we can't do very high-speed communications with this because our typical high-speed communication signal has a much larger peak to average ratio. Looking at what causes that, ultimately, what we're doing is we're encoding our amplitude information in the width of the pulse. So here we have bandpass pulse width modulation represented in a more mathematical form. What we're doing is we're encoding pulse width and pulse position in terms of the amplitude is encoded in terms of the duty cycle, and the phase is encoded in terms of where the edge of the pulse starts. So the frequency that this operates at is inversely proportional to the period. So the center frequency would be 1 over the average period of the pulse width modulation. And the amplitude that we see is given to us by this, the fundamental Fourier component, which is 4 over pi times sine of the duty cycle times pi. And we see the duty cycle is given to us by the pulse width, tau, divided by the average period, t. So here we see a couple of things. So one, we see if we change the input duty cycle, we do see the amplitude changing, but we also see a rise in harmonic content over that expected duty cycle. This isn't much of a problem for power amplifiers because power amplifiers are tuned elements. They have a bandpass filter that's inherent to the network. So the filtering selects just the fundamental frequency component and attenuates the harmonic content. Ultimately, what we're looking for is this more efficient than a linear power amplifier over the expected signal envelope? So here we have an efficiency comparison of ClassE power amplifier, which is our switching amplifier, and a ClassB amplifier, which is our linear power amplifier. And we see that if we vary the duty cycle to change the output power of the ClassE device, the efficiency characteristic is always better than a linear ClassB amplifier. So we expect that its average efficiency would be better as well. But as I have kind of motivated, this is a problem because we have a limitation to small peak to average power ratios. So why did I show this? Well, it's kind of interesting for some niche applications that I'm looking into, which have to do with low power sensor PAs, because these operate at lower frequencies and we can get some nice power control and things like that. A second technique that I worked on is the bulk of my PhD work was on a technique called envelope elimination and restoration, EER. And what's interesting about this technique is it was first proposed in 1952 by Leonard Kahn. So the message is that we can find some pretty interesting things if we just look in very old literature. This is a modern digital implementation of a Kahn EER technique. And what I mean by that is we have a digital interface that happens very close to the power amplifier. So the digital interface would happen somewhere along the line I'm tracing right here. So what do we do in the EER technique? Well, we take our complex communication signal from its Cartesian mapping and change it to a polar mapping. We have an envelope component that corresponds to the envelope of the communication signal, and a phase component which just corresponds to the phase modulation component of the input signal. We send the phase component through an up converter and limit it, and this drives the gate input to our power amplifier. So this drives the switching interface to the power amplifier. And we simultaneously take the envelope component, digital to analog convert it, and use this to supply the power amplifier's voltage supply. And this is an interesting technique because we know that power amplifiers are most efficient when they're operating near their saturation point. So what we're going to do by changing the supply voltage of the power amplifier is to change the is to try and keep the transistor saturated all the time. In other words, try and keep it closer to its maximum efficiency operating point. How do we do that? Well, we use what's called a low dropout regulator. So a low dropout regulator is also called a series voltage regulator. And what happens is we use an op-amp that controls a PMOS pass transistor through a negative feedback loop. And an op-amp is always trying to force the two input terminals close to one another via that negative feedback action. So what we would find is that the input envelope going into the inverting pin forces the non-inverting pin to follow it, and so we would see a replica of that input envelope at the output. One thing that we see about this particular supply modulator is that its efficiency scales linearly with respect to the output voltage. So it's definitely going to beat the square law that we see with the linear power amplifier. And of course, the ideal maximum efficiency is 100% because ideally the output voltage can go all the way up to the supply voltage. So one thing that I investigated was when I was working on my PhD was, can we extend this to more than 2 supplies? So what if we could create a situation where we had 2 peaks? In other words, what we're trying to do is to shape our efficiency characteristics so that it's better, or so that it's more well matched to a modern communication signal. So here, what I propose is that we have some kind of bias control circuit that will cause us to draw current from transistor M2, which has a supply voltage that's some scaled replica of our nominal supply voltage, when the input signal is small, and if the input signal rises above this scaled replica of our supply voltage, we draw current from the full scale supply voltage. And this should give us 2 peaks in our efficiency characteristic. 1 peak at VDD over X, our scaled supply voltage, and 1 peak at VDD. One question that would naturally be asked is, can we extend this to more than 2 supply voltages? If this is a good thing, can we extend it to more than 2 supply voltages? And of course the answer is yes, we can, but we get some diminishing return because we are always consuming some energy in our bias control circuitry and our op-amp that controls this feedback loop. So we can extend it to more than 2 supplies, but it starts to get a diminished impact on our performance. Here's the goal, however, is that we have an efficiency performance that's shaped closer to our expected communication signal envelope. So here's that same Rayleigh envelope that we saw earlier for our typical Wi-Fi signal. And we see a linear power amplifier characteristic in our ClassG dual supply voltage power characteristic. And one thing that we're looking at ultimately is the average efficiency better. So how do we calculate average efficiency? Well, if we take our efficiency and we weight the efficiency characteristic by the probability density function of the communication envelope, we would be able to calculate an average efficiency. So I have the red dot, the red square here and the red circle representing the average efficiency for the dual supply power amplifier and the linear power amplifier respectively. And we see that we get ideally about a 10x improvement in average efficiency. So quite good. This is an implementation that I did while I was at University of Washington. And what we see is we use a multiple supply modulator, in this case 2 supplies, to supply an RF power amplifier's voltage supply terminal. And we create a couple of, we create a Cartesian to polar conversion in software that ends up driving the input to this system. The graphical representation here is when the input signal is small, the current is being drawn from a small voltage supply. And when the input signal is large, the current is being drawn from a large voltage supply. So this is the ClassG modulator circuit. So what it consists of is 2 low dropout regulators operating in negative feedback with a comparator and pass transistor logic that controls when current is being drawn from either VDD divided by X or VDD. So we see if the input voltage is less than VDD over X, current is drawn from that small voltage supply and fed to the output. And if the voltage supply, if the voltage input increases, current is drawn from our larger voltage supply and fed to the output. One problem that happens when we have 2 control loops that are fighting one another, which would happen at the point that near that small supply voltage, is that the loops might tend to fight each other. So what I did in this implementation was to put a pole at the gate of transistor M1 and M2. So the pole uses a resistance R1 in parallel with the parasitic gate capacitance from the transistor. And then what it does effectively is slows down handover from one loop to the other loop so that we don't see any glitching in the supply voltage. So here is what would happen if we saw a glitch and what happens if we mitigate that glitch. So if we don't have that switching pole at the output, we would see if our signal was trying to change from a high supply voltage to a small supply voltage, a glitch as it made that transition. By putting that switching pole at the gate, we soften that glitch. And what this does is helps us to meet our metrics for performance, for fidelity when we're amplifying signals. And we'll look at those in a moment. But things like error vector magnitude and spectral performance. Here's the ClassE power amplifier and driver circuitry that was implemented. So the transistor switch consists of a thin gate device and a thick gate device, as we showed earlier. And we use spiral components on chip to realize the inductors and metal capacitors on chip to realize capacitors. We use a tapped inductor match so that we can make L1 and L2 inside of a symmetric winding, which saves us a little bit of area. One thing that was interesting here is that the driving circuitry is all done in a very digital fashion. So we use a typical taper of 2 increase in the size of the driving transistors to give us our best logical effort to drive those switches. One problem is that we consume a lot of power to charge and discharge the parasitic capacitance on the switching transistor. So we've reduced that by adding a shunt inductor which resonates some of the capacitance from that transistor at the RF frequency. And in order to make sure that this doesn't cause any bandwidth limitation in the circuit, we make sure that the bandwidth at the internal node here is the same as the bandwidth at the external node. And of course, all the design is optimized for power, speed, with efficiency as the most important metric. So here is a 130 nanometer implementation of the ClassG power amplifier. We see the output power stage here, the power amplifier, all those driving transistors, and the interstage inductance that I just talked about right here, and our supply modulators on either side of the power amplifier. And of course, delay paths are matched very well between these so that you see similar delay between the 1.65 volt supply and the 3.3 volt supply. This looks quite large, 2 millimeters by 2 millimeters, but the active area is only in about this portion of the chip. We were kind of pad limited when we were interfacing with the chip. So it's quite amenable to integration in system-on-a-chip architectures. Ultimately, what we want to see is this better than a linear power amplifier? And so I think we have some justification that it is. So we see that by changing the supply voltage, we get a relatively linear variation in the envelope of the over the envelope of the signal. But what we were really looking for is we wanted to see 2 peaks in efficiency. We wanted to see a peak in efficiency at the peak output voltage and a second peak in efficiency at some lower scaled version of the output voltage. And of course, we do indeed see that. Now, we don't get that 100% performance for the ideal amplifier, but if we compare this to a Class B power amplifier, it's significantly better than that linear power amplifier. Looking at the average efficiency of this system, we found that for a Wi-Fi signal, the average efficiency was around 22%. Now, if we compare this to even an ideal Class B power amplifier, the average efficiency would only be about 7%. So quite good compared to what we could get with a linear power amplifier, even an ideal linear amplifier. Looking at the dynamic measurements, we have to make sure that we can actually demodulate the signal. And so here we have a constellation diagram, which basically tells us how close our demodulation comes to finding the ideal vector point. And here we see an RMS error vector magnitude of 2.5%. The specification for Wi-Fi is about 5.6%. So it definitely beats that. And more importantly, we don't want to go to jail when we manufacture radios, so we have to satisfy the FCC's condition of not violating the spectral mask. So here we have a spectral mask, and we see that our communication signal is always under the spectral mask. And these measurements were performed at 2 gigahertz. So on to what I think is a much more exciting architecture in terms of its ability to be reconfigured is the switch capacitor power amplifier. And this is an architecture I worked on with a grad student, Sangmin Yu, while I was at University of Washington as a postdoc. So first we'll look at digitally modulated power amplifiers. What's a digitally modulated power amplifier? Well, we're going to take an input code A, which is going to come into the amplifier in the form of some digital code word. So it'll be a sequence of bits. And the sequence of bits is going to turn on unit power amplifiers that aren't designed to output very much output power. But if we turn on a lot of them and sum their outputs, we can get quite a significant output power. So there were 2 kind of competing architectures that were introduced in the last couple of years, one by Kavusian in 2007 and one by Presti in 2009. They both more or less use the same topology, where the power amplifier is implemented as a unit current cell, and that unit current cell is summed at the output node. The problem with using a unit current cell-based digital power amplifier is that ideal current cells need to have infinite output impedances. Of course, we can't realize infinite output impedances with a real current cell, so we have an accuracy and efficiency trade-off. In order to get a large output impedance, we can do things like cascoding the transistor or giving the transistor more voltage headroom. But this gives us a lower efficiency performance. Another problem is that we typically get a fairly saturated output characteristic with respect to a digital input code. So here we see a linear region and a saturated region. And what this means is that we need a few extra bits in order to do some kind of digital predistortion so that we could correct the output code with respect to input code and get a linear characteristic for linear amplification. It's important to note that the ideal efficiency scales with the square root of the output power, and this means that this is better than the efficiency trade-off that we get with a linear power amplifier, which is what we want to see. So what does a switch capacitor power amplifier look like? Well, we can take a switch and switch the bottom plate of a capacitor and then use some filtering to select a harmonic. So it's a typical switching power amplifier. And in fact, if we look at this architecture, it ends up looking like a Class D power amplifier. And we'll look at that in more detail in a moment. But it's a typical Class D power amplifier. What we note are a couple of things that are favorable towards using this architecture. So one, capacitors and switches are native devices in CMOS. We don't need anything extra to be added. And we have good switching performance in CMOS. We don't have very good current cells in CMOS. So that's something to keep in mind. One thing is that, that we can take this single capacitor and array it into a bunch of individual smaller capacitors where the total capacitance is just the sum of all these capacitors in parallel. Each capacitor can either be connected to ground VDD or switched between VDD and ground. So our supply voltage VDD and our ground supply voltage V ground. One nice thing to note is because VDD and ground are signal grounds, that if I look back into the array from the bandpass matching network, I see the same total capacitance. So I don't see any resonant frequency shifts with this architecture, which means that as I change my digital input code, in other words, as I either enable or disable some of these capacitors, it operates at the same frequency. We'll see the efficiency performance is very high over a linear envelope. So here's the functionality of the switch capacitor power amplifier. So in the first case, I'm going to input a maximum code. In other words, what I'm going to do is switch all 4 capacitors in this bank at the same, between VDD and ground. And at the output, I'd expect then to see the top plate follow that switching behavior. Because I can't change the voltage instantaneously across the capacitor, if I increase the voltage at the input node, the output node has to increase by the same amount. So after the bandpass matching network here, bandpass matching network acts as a filter. It selects the fundamental component. So if I were to do a Fourier expansion of this square wave, I'd get a bunch of harmonics of that. I design my bandpass matching network to select just the fundamental. So I get a nice sine wave at the output, ideally. Now, in the second case, I'm going to input a minimum code plus 1. So it's going to be 1 LSB plus 1 on the digital input code. So the LSB is going to cycle between VDD and ground. It's going to switch between VDD and ground. And all of the other capacitors in the array are going to be held at a fixed potential. So what happens here is when this switches, the the voltage across this capacitor instantaneously goes to VDD. And then when it switches to ground, the charge on this capacitor has to redistribute across all the array in order to maintain conservation of charge, so a fundamental law of physics. And so once that conservation of charge happens, the output voltage redistributes to some lower voltage. And if we filter that lower voltage, we would see a corresponding change in our output voltage. So we see that we have some degree of control of our amplitude just by changing the digital code word that we apply to the power amplifier. So we can look at a Thevenin equivalent circuit of this network. And so if we take our capacitor bank and we have, and some of these capacitors we're switching, so we put a voltage source on them, and some of them we're holding at a fixed potential, so we tie them to ground. We see that we get a digitally controlled input voltage. So here our input voltage is proportional to the number of capacitors that are switching, little n, divided by the total number of capacitors in the array, big N. Importantly, though, we see that the capacitance is always constant. So that means that the resonant frequency doesn't shift. Looking at output power, we want to see that we can control output power linearly with our input code. So here we find that the output voltage is set by that ratio of switching capacitors to total capacitance. We have a fundamental Fourier coefficient for this digital square wave gives us this 4 over pi term. So if we look at an approximation for the output voltage, if we assume that we have perfect filtering for the higher order harmonics, we get an output voltage that's linearly proportional to the number of capacitors that we're switching. And correspondingly, if we took the RMS value of this voltage and divided it by the output resistance, we would find the power that we get. Now, the switch capacitor power amplifier also dissipates power, so it's not going to be 100% efficient. So how do we estimate the efficiency in the switch capacitor power amplifier? Well, we find that most of the loss occurs due to switching relatively large gate capacitances. So we have our typical CV squared F loss in our switching devices. If we look at an equivalent circuit here and we assume that we have a sharp turn on and turn off time, so we have a very sharp rise and fall time, then our inductor has to behave like a current source because we can't change current across an inductor instantaneously. Much like we can't change voltages across the capacitor, we can't change current across an inductor instantaneously. So our inductor at RF frequencies behaves like an RF current source, and we can basically assume that it's an open circuit for our analysis. So looking into the capacitor array, this is the total, the total amount of capacitance we see is the series combination of the capacitors that are being switched to the capacitors that aren't being switched. So we can estimate our power consumed in the array with this estimation shown here. Now what we want to see ultimately is, do we, the digital power amplifier beats the linear power amplifier. Can we beat the digital power amplifier with this technique? And ultimately it has to do with how well we can make our matching network, how low loss we can make our matching network. So this has to do with the loaded quality factor that we can achieve in the matching network. So one definition of loaded quality factor is 1 divided by our frequency times the total capacitance and times the resistance. The resistance is set based on how much output power we want to get. So if we choose a given resistance and we have a maximum loaded quality factor we can expect to achieve, we have a given size for our array capacitance. Now one thing that's important to note is that we can't achieve very high quality factors on chip with CMOS transistors because inductors are very lossy. But a typical value we can achieve for a loaded quality factor would be on the order of 3. So here's the efficiency characteristic of a switch capacitor power amplifier with a loaded quality factor of 3. And we compare that to the digital power amplifier with the magenta characteristic. And we see that it's much better than the digital power amplifier, even with a relatively low loaded quality factor. Of course, if we look at practical efficiency, we have a few other losses that we have to take into account. So what are those other losses? Well, we have some attenuation due to loss in the switch. The switch has finite on resistance, and the inductors have some loss factor. The switch has parasitic capacitance that we have to charge and discharge every cycle, and our switch drivers have parasitic capacitance, and any kind of clock distribution we have to do for the circuit has parasitic capacitance. So we see an estimate for all of these losses. One thing to take into account here is that all of these losses benefit from scaling because all of these are due to switching parasitic capacitance, and parasitic capacitance reduces with every successive process generation. And on top of that, supply voltage is reduced. So this is one of the truly unique power amplifiers that actually benefits from scaling to some degree. So how do we lay this out? How do we design this? Well, in the implementation that we made, we have a 4-bit unary capacitor array, which is chosen for superior matching. This gives us very good linear performance over our digital input code. But in order to get a little bit of coarse resolution control, we have a 2-bit binary capacitor array. Of course, if we needed more bits, as we might need for cellular kind of accuracy, we could add more unary bits, or we could try to use traditional DAC techniques such as a C2C ladder. And one thing that we're going to note is that we're going to take a very digital friendly design for this. We're going to design each of these arrays to be pitch matched to a capacitor, and we're going to design them so that they're just individual cells. So if we wanted to add additional bits of resolution, very simple. We just add another slice to the design. One thing that we need is a relatively high output voltage. So we do this by cascoding transistors, and we operate our NMOS transistors from a different supply voltage range than our PMOS transistors. And this allows us to switch the transistor here safely over a voltage range of twice the supply voltage. So this is important because it allows us to operate at a higher output power with a smaller output resistance, or with the same output resistance. We use thin gate devices in this. Instead of using a thin gate, thick gate cascode, we use thin gate devices in this because speed's very important. And one other thing that we do is separate the control. We have non-overlapping clock generators so that there's no point where the PMOS devices are on at the same time as the NMOS devices. In other words, crowbar current doesn't dissipate through the transistor from the supply voltage through to ground. This is a schematic of the implementation. This is a single-ended schematic implementation. The actual implementation was done with a fully differential power amplifier. But we see this kind of bit slice technique. Each of these slices is designed like is shown in the upper left-hand corner. We have a non-overlapping clock generator that takes the phase modulation of the input and clocks all of our digital bit slices, and a binary thermometer decoder which converts our digital input code into a linear output code to drive all of these bit slices. This is an implementation of that switch capacitor power amplifier. And one thing that is important to note is the capacitor array, switch drivers, and logic are all implemented in about half the area of the output matching network. So, what I said about adding additional capacitors to the array, adding additional resolution, wouldn't actually hurt us in terms of area because our output matching network's relatively large. So looking at the performance, again, we want to compare this to what we could do with other techniques. So here is our output power versus input code. And we see a very linear characteristic. Of course, it looks like it's saturating, but we're plotting this in the log domain. And more importantly, is this more efficient than our linear power amplifier? Does this beat the linear power amplifier? So if we have a similarly scaled linear power amplifier, the switch capacitor power amplifier beats the linear power amplifier over all performance, over all output power ranges. And we achieve a peak efficiency of 42%. And importantly, at power backoff, the efficiency is only reduced by just over 10%. So this tells us that this would be very efficient over a typical communication signal envelope. Looking at a couple of other performance metrics, the nonlinearity in the PA has to be measured because this is ultimately going to set what type of output power we can achieve. And we get fairly linear characteristics for AM to AM distortion, the portion of the amplitude signal that's translated into nonlinearity, and AM to PM distortion, which is the portion of the input signal that's translated into some kind of phase shift. And important to note is that because of the relatively soft nonlinearities, these are fairly easy to digitally correct. Because we have a relatively low loaded quality factor, what this means is that we get a relatively wide bandwidth performance. So this is very amenable to some kind of tuning architecture. And of course, we have to look at this over dynamic performance as well. So looking at the signal constellation, we achieved an EVM error vector magnitude of 2.5%, which was very similar to that ClassG architecture that I just showed. The problem is that the switches weren't very well matched, so we got a little bit of clock feed through at the digital code modulation rate of 160 megahertz. In a subsequent version that we'll be presenting at RFIC this year, we've fixed this clock feed-through problem. And also, we have a little bit of spectral, exceeding the spectral limit due to mismatch between the phase and amplitude path, which has also been fixed in a subsequent version. So looking at where we go from this, how do we make this, we have a fairly reconfigurable architecture already. We can change the number of bits dynamically that we need to operate on in order to achieve certain degrees of linearity for different communication signals. So where do we go if we want to make a software-defined radio? Well, we need some frequency reconfigurability. The RF power amplifier, for reasons that I've already shown, is a tuned element. We have to have that bandpass filter at the output because the PA is not very linear. And the other reason is that we have to transform an antenna impedance, which might be 50 ohms, down to a smaller impedance, maybe on the order of 5 ohms if we want to get a lot of output power out of a power amplifier. So the power amplifier is tuned for those reasons. So we need an ability to tune passive elements. So what was recently proposed in order to do this was a high voltage tolerance switch, basically where we float all terminals of the transistor with respect to the RF frequency. That way we can tolerate high voltages across these switching components. And if we do that, we can come up with a switching topology that looks something like this. We have a bunch of series capacitors. So if all of these transistors are turned off, we have a small capacitor because we're combining capacitors in series. Alternatively, we can selectively turn on these switches to short out the capacitances and increase the capacitance as a function of some kind of digital code. Now we can do a similar thing with an inductor, but inductors are a little bit trickier because inductors are very lossy on CMOS because we make them with spiral structures and they end up having a lot of bulk eddy current losses. So one thing we can try is to use slab inductors to minimize the bulk eddy currents that flow in the substrate. The other thing that we get when we use a structure like this is this slab inductor doesn't have any overlap metal. If we have a spiral structure, we wind it in on itself, then we have to get the internal winding out to the outside somehow. So we usually go through a via down to a lower level of metal and then bring the output out. That incurs a lot of loss and also lowers the self-resonant frequency. The slab inductor doesn't have that drawback. One drawback with the slab inductor is that we can't get as much inductance because we don't have the same kind of flux linkage we get with a spiral shape. But nonetheless, we can make a fairly low-loss tunable inductor using this technique. So how do we make a frequency reconfigurable switch capacitor power amplifier? Well, we know we had this fundamental design equation. If we wanted to get a certain output power, we have a certain resistance we have to present to the array. And if we want, if we have a certain loaded quality factor, peak loaded quality factor that we can achieve, then we know what capacitance we need. So if we want to tune this capacitor array, we basically just select, for a frequency of operation, we select the capacitor size. But then we'd have to tune the output matching network components in order to create the proper resonance at the desired output frequency. So one implementation might look something like this. We take a bit slice, we replace the capacitor with this tunable capacitor, and we replace our matching elements with a tunable slab inductor and tune the frequency as dictated by where we want to operate. Looking at a couple of other possible applications are low power radios. So one thing that we might want to do is to try a targeted wake up for low power sensor networks. So sensor radios need to be low power because we're going to try and deploy them for a long period of time. And what that means is that we can't operate them all the time. So one thing we could try to do is some kind of passive technique where we charge an RF to DC converter and then run a advanced D modulator. So advanced D modulator works as follows. We have a two-stage ring oscillator and we injection lock it to an incoming RF signal that has FSK modulation on it. So if the frequency modulation is above the natural operating frequency of this advanced D modulator, it might cause the in-phase component to pull upward, the out-of-phase component to pull downward, and then we'd get some kind of data out of it if we multiplied these two waveforms. Conversely, if the input frequency went down, the output frequency would go up, and we'd get a different output from the passive mixer here. I've got a grad student working on this right now, and he's already shown that he can achieve sensitivities in the order of minus 60 dBm operating from a 1 volt supply with a 30 microwatt oscillator. So very conducive to batteryless wake-up systems. Last year I worked on some antenna interfaces. So one of the problems with wireless sensors is that we typically make them using relatively conventional power amplifiers. I noted that on a couple of recent implementations, the global efficiency for the transmitter was quite low. And one of the reasons is the power added efficiency for the power amplifier was low. So in a recent implementation at University of Washington, one of the power amplifiers was 16% efficient. So I worked with Karthik Natarajan to build a ClassC power amplifier. And one interesting thing about a ClassC amplifier, we haven't discussed it, but the peak efficiency is ideally 100% when the output signal goes to 0. So that's typically bad. But in a sensor network, we don't need a lot of output power, so we can leverage the fact that we get a peak efficiency number for a relatively low output power in this ClassC topology. As I noted, this is perfect for sensor networks where we might have 10 microwatts to 1 milliwatt level output powers. The problem with this architecture is that we need relatively large inductors in the drain. And so in this particular version, we had to implement these inductors with bond wires. We'd like to implement everything on chip if possible. So I have one student right now looking into whether we can replace the bond wire and spiral inductors with an active inductor, which uses a transistors, which uses a phase shift trick with a transistor. It's pretty interesting. So now I'll wind things up and take questions. First, I'd like to say that I think I've shown a few interesting architectures that provide a very reconfigurable interface for digital transmitters. We've basically shown that we can kind of convert digital data converters into power amplifiers to work in these architectures. We have a couple of reasons to do this. One for the software-defined radio angle, but another thing is that we have a selfish motivation to do this, is that we don't want to have to charge our batteries very often. We'd like to be less tethered to the power supply grid. But an altruistic reason is that radios are becoming very energy hungry on that grid. I did a back of the envelope calculation about 2 years ago, and at the time, before smartphones had become so ubiquitous, the power consumption from the electrical grid, I had an estimate of about 600,000 US homes annually, which is something about the size of the Salt Lake Valley. So our energy from our wireless devices is increasing, and this is problematic. So we can be altruistic and try and decrease that by not having to charge them so often. And then, of course, I've shown that CMOS is a fairly poor transistor, a fairly poor transconductor. So why don't we try and take advantage of what CMOS scaling gives us, which is good switching performance. And of course, we can also start to think of energy efficiency in terms of our low-power wireless sensor networks as well. So with that, I'd like to acknowledge some of my collaborators, my current students at Rutgers, Predrag Spasojevic, a professor at Rutgers, and then former collaborators at Intel and University of Washington. And I'd like to thank you and take your questions.
Questions? Would you please go back to the slide where you showed the maximum voltage stress? You got a number of 3.5 times of the VDD.
Yeah.
How do you get that? Because doesn't it depend on the duty ratio?
Pardon?
Don't you think it depends on the duty ratio of the switch? Because if you switch it at 50%, then it will...
It does, and it increases a bit with the pulse width modulation, so that's actually another problem. But again, we're softening that by using a smaller inductor.
Does it depend on the inductor size, or is it exclusively depend on the switch?
No, it also depends on the inductor size, yeah.
Okay. consider the switching, like the charge loss, because when you actually parallel two capacitors with dissimilar voltages, you cannot get more than 50%.
Right. If you have any resistance in the switch, yes. And I mean that's why we can't achieve a peak efficiency of 100%, but we can get it close to 50% at peak, which is still better than we can get with actually most linear amplifiers. Most linear power amplifiers operating this frequency range.
Have you considered it in this equation?
Yes, it is. Yeah. When we factor all of the power loss in the capacitor array, we end up with this alpha factor basically is where we put that. That is alpha estimates the finite on resistance of the switch.
Okay.
Yeah.
And could you please go one slide where actually the step inductor, the physical,
Yeah.
this slide. Is there any consequence when you actually short circuit a capacitor? Can you do it real time, or
No, we wouldn't necessarily try and do this for any kind of real-time application. We can't do this very quickly because we get some kind of transient in the response. But we typically aren't trying to change frequency bands very quickly. We're just trying to change our output voltage with whatever our modulation envelope is. So, yeah, we can't tune this instantaneously to a new frequency, but that's not what a software-defined radio would typically be doing. So it's not much of a consideration. I mean, another thing that we can do is also try and use this to find a more optimal load condition for strong interactions with the antenna. So, again, those things happen more slowly.
Thank you.
I had a question on the voltage stress. Why not pick a different duty cycle that has a lower voltage stress?
We could do that, but I mean, if it depends on what type of modulation we're trying to actually force through. The modulation we're trying to put through the device is going to basically dictate what the duty cycle has to be. We get a peak output power for 50% duty cycle, and it rolls off for a smaller duty cycle.
Right. So why not tune it for a different duty cycle than 50%? You tuned it.
I had two, when I taped this out at Intel, I had one that was tuned for a 25% duty cycle, more optimally for a 25% duty cycle, and we saw fairly similar performance. It actually didn't give us too much leverage. And part of that is that we're getting less output power out, so the output power is low, so our efficiency is kind of, we still have a lot of digital circuits that are switching that consume power, so we get that kind of diminishing return on our total efficiency.
Okay.
So.
And I was also wondering in the envelope one, why not use a switch DC power supply as opposed to an LDA?
That's actually something that I'm very interested in doing, and one of the reasons there's a class of amplifier out there that people have hypothesized called a ClassH amplifier, where they do use a continuous DC-DC converter to try and provide that envelope, and that's something that I'm very interested in working on. Yes.
So that's the resistance you want to push the power into.
Yes.
But then if you look at the 2 nanohenry inductor, let's assume that the kilo 3 and 2 gigahertz, it'll have a series resistance of about 8 ohms.
Yes. Actually, we get better, typically better quality factors.
Right? You probably get about 5 ohms. So you have a 5 and a 5, so it becomes 10 ohms.
Yes.
And how much resistance do you have associated with the switch?
The switch is under an ohm.
Under an ohm?
Yeah.
How large?
Total. Well, on the ClassE amplifiers, those were about 2.5 millimeters of gate width. But we used multiple fingers. The total thing ends up being very small. And, I mean, you can see that with the layout. This is 2.5 millimeters of gate width, and it's implemented right here.
So can you say that the low key of the inductor is the series resistance?
That's what causes the biggest problem with power amplifiers. Yeah, that is the problem. If we want it to operate with high output power, we need a relatively low termination impedance. And what ultimately dictates that is that we're going to get some kind of voltage division. Yeah. And So, I mean, one solution to that is to use power combining techniques to try and increase the optimum termination impedance for, by using some kind of power combining technique. And that's we actually did present a paper at RFIC last year on a power combined switch capacitor power amplifier that was addressing that exact problem. Yeah.
Any other questions?
Maybe one question. Your polar amplifier work is very interesting. There was a big push on that, I think, maybe 10 years ago.
Yeah.
Yeah, a lot of effort. But you alluded to some of the challenges there in mismatch delays,
Yes.
and phase noise, and a lot of this stuff impacted, I think, manufacturability ultimately.
Yes.
Maybe limited the commercialization of some of that technology. So I just wondered if you're, the tool supply design was interesting. I just wondered if you were able to, if this would actually make you be more susceptible to some of those.
Well, so again, we have to make sure that we have fairly good matching, especially between the two different supply paths, since we really can't lay them out on the same side. So it does take a lot of effort to make sure delay paths are mismatched on that. It's not any more susceptible to delay mismatch in the amplitude and phase path, but one thing that actually is very difficult here is we're trying to align generators that are off chip going through a couple of meters of cable runs, and that's where the real challenge is. On chip aligning phase, we've seen a couple of reconfigurable DLL techniques that allow us to calibrate the delay between the envelope and phase path, and so I think over the last couple of years they've really kind of solved that particular problem using calibration. But yeah, in this case, I don't think we see any additional problem. Matching the delay in envelope and phase, we need to less than 2 nanoseconds at 2 gigahertz. And the biggest problem for us is because we don't typically integrate the phase modulator and amplitude modulator together on the same chip, you have to match these generators. And that's actually quite an interesting challenge. But Agilent generators all give us a marker on the output of them. So what we do is you output a marker on 2 generators, and you have an oscope, and you can line the markers up, and then the 2 generators would be synced in time just by calibrating a delay. In this particular case, we didn't have 2 Agilent generators. We had a Tektronix generator and an Agilent generator, which is why we couldn't get them. Agilent and Tektronix don't like to play together so well. So, yeah.
Okay, one last question.
I missed the one thing. One of your slides you showed that you take the information between the polar domain.
Yes.
And in the phase, you go into a digital mixer.
Yes.
What is the component that you're mixing?
In this case, we're actually just using the generator. In an actual integrated version, what we would probably do is use a delay locked loop as the phase modulator. And in fact, at ISSCC this year, they had an outphasing transmitter. Intel presented an outphasing transmitter where they did just that. They have a wideband delay locked loop that they use as the phase modulator. In our case, that was done with a signal generator. Yeah.
Okay, so given the time, if anyone has any more questions, please come down and talk to Jeff. So let's thank Jeff again for his
Thanks.